Close your eyes if you like. Let your ears carry you and drift. Here by the lamp, the book is already open to a quiet first page. Tonight, we're visiting a question that's gentler than it might seem at first. It's the question of how life began on Earth. We can let it invite us in slowly, without rush. The chapter we're reading tonight isn't finished. Some pages are written in confident ink, mainstream ideas most researchers would agree on. Others have notes penciled in the margins, where experiments are ongoing, and a few lines appear very faintly in the speculative what-if voice. We'll turn each kind of page together. We'll always notice what kind we're on. There's no need to hurry. The question has waited this long. It can wait for us too. On the page in front of us, we can underline one word: abiogenesis. That's the term scientists use to describe the origin of life from non-living chemistry. Not evolution. That's the chapter about how life changes and diversifies once it's already here. Abiogenesis is earlier. It's about the shift itself, and transition might be the right word. In the working picture, life didn't switch on in a single moment. It emerged gradually as chemistry grew more complex, more organized, and more able to copy itself. The boundary between not life and life may not have been a sharp line. It may have been a soft threshold we crossed without noticing exactly where. We can let that definition rest quietly on the table, under the warm light. Back in the chair, we can hold the thesis like a penciled note in the margin. Under the right conditions, chemistry began building more complex molecules. Those molecules organized into systems, and eventually, those systems crossed a threshold. They could copy themselves, pass on variations, and respond to selection. That threshold is where the language of biology begins. Before that, we're still in chemistry's domain. This wasn't goal-driven. Chemistry wasn't trying to become life. But early Earth may have made that pathway possible. We don't have to settle the argument tonight. We can leave it penciled in for now. We can imagine 2 dates as bookmarks, then return to the line we're reading. Earth formed about 4.5 billion years ago. The earliest widely accepted fossil evidence of life, stromatolites, built by microbial communities, dates to roughly 3.5 billion years ago. So there's a wide window of time. Somewhere in that span, the transition happened. The rock record from that early stretch is sparse. Much has been lost or altered. So the picture we're working with is incomplete, pieced together from fragments. Current evidence suggests early Earth may have been cooler and wetter than once believed. Oceans may have existed even in the Hadean period, but the details are still being refined. We can set those bookmarks on the shelf and let the room stay quiet. On the tabletop, we can set down a short list titled Parts and Assembly. The building blocks of life: amino acids, simple sugars, nucleotide bases, can form without life. Lab experiments have shown this under early Earth-like conditions. So the parts themselves can arise through abiotic chemistry. Carbon's flexibility is key here. It can form stable chains, rings, branching shapes, a full palette of molecular structures. But having the parts isn't enough. Assembling them into a system that works is the deeper challenge. Connecting those parts into polymers, organizing those into functional units, getting those units to replicate. We can smooth the page flat and keep those two words in mind: parts and assembly. In the library room, we can take down two folders from the shelf. One labeled isotopes, one labeled stromatolites. In ancient rocks, carbon isotopes show a pattern called fractionation. In some cases, that's interpreted as a possible signature of biological processes. The interpretation is debated, especially for the oldest samples, but it's one tool for inferring early life. Stromatolites, those layered structures dating back about 3.5 billion years, are more direct. They're widely accepted as the work of microbial communities, slowly building layer by layer. These are two imperfect but helpful handles for reaching into deep time. Then we can return both folders neatly to the shelf. On the page, we can draw two brackets, one for information, one for catalysis. Side by side, here's the central tension. DNA and RNA carry instructions. Proteins do the work. They catalyze reactions, build structures, make things happen. But DNA and RNA need proteins to replicate, and proteins need DNA or RNA to be encoded. It's a loop. Each depends on the other. So the question arises, which came first? Or did they arise together in some way we haven't yet uncovered? This paradox sits at the heart of most origin of life research. It's what drives many of the current hypotheses. We can close that bracket gently and turn the page. Back by the lamp, we can keep a bookmark on one word: RNA. The RNA world is a widely used working idea. It suggests RNA may have once carried both roles, information storage and catalytic activity, before the DNA-protein partnership took hold. Lab work shows that RNA molecules can act as catalysts. These are called ribozymes. In carefully designed experiments, some ribozymes can even help catalyze steps in their own replication. This is proof of principle, not a replay of history. The lab setups are controlled. The ribozymes are limited. There's still a long way to go. But the idea isn't ruled out. RNA could, in principle, bridge information and function. We can let the bookmark rest, without asking it to hold the whole chapter. We can picture a simple diagram on the page, then come back to the quiet room around us. One setting scientists are exploring is alkaline hydrothermal vents. Current evidence suggests these vents may provide steady electrochemical gradients, proton gradients, relevant to early chemistry. The details are still being tested in models and lab setups. We can shelve that diagram as one working idea. On the table, we can lay two open pages side by side, one for vents, one for wet-dry cycles. Another possible setting focuses on surface areas where things periodically get wet and dry. These cycles might help molecules link together by concentrating them and encouraging reactions. It's a different piece of the puzzle. It focuses on building longer chains, on polymerization. The two ideas aren't necessarily in conflict. Different steps might have happened in different places. We can leave both pages open halfway. No need to choose tonight. By the window, we can hold the idea of a boundary, like the edge of a page, a line between inside and outside. At some point, enclosure started to matter. A protocell, an organized cluster of lipids, can form a compartment. It separates the internal chemistry from the world outside. This is often treated as a key condition in origin scenarios. But how that boundary began working with replication and metabolism remains an open question. Certain molecules, called amphiphiles, can self-assemble into tiny vesicles. That part we can demonstrate in the lab. What's still unfolding is how those compartments became part of life's machinery. We can rest the idea of the boundary on the page and leave it simple. Back by the lamp, we can note one thought in the margin. Heredity changes what the chapter can say. Once a system can replicate, pass on variations, and have those variations influence survival, then heredity is in play. That's when the language of evolution begins to apply. Before that, it's still chemistry. Perhaps very organized, maybe even self-sustaining, but not yet shaped by Darwinian selection. Marking that threshold helps us be careful. It keeps us from using evolutionary terms too early. The transition into life is not the same as the diversification of life. We can leave that note where it is, without pressing harder. In the reading room, we can trace one line on the page labeled Shared Ancestry. Then return to the chair. LUCA stands for Last Universal Common Ancestor. Not the first life, just the most recent organism from which all current life descends. The one whose lineage made it. The shared genetic code in all known life points to common ancestry. That's broadly accepted. From there, scientists infer a few things. LUCA was likely anaerobic, maybe adapted to high temperatures, with a small genome. But LUCA came after life began, possibly long after. There may have been many other early lineages that didn't survive. We can place that line gently back into the book, without stretching it too far. On the page, we can circle the phrase, "still being tested," then glance back at the steady lamplight. The early rock record is incomplete. Much of it has been altered by metamorphism. Some findings, like carbon inclusions in 4 billion-year-old zircons, are debated. Signal or noise, biological or chemical. There's a limit to how far back we can infer. We can build a picture of LUCA from life's shared features, but earlier steps, first compartments, first replicating systems, leave much fainter traces. What could help? Better preserved early rocks, more refined lab chemistry, clearer chemical markers that distinguish life from non-life. We can leave that uncertainty on the shelf, open, not closed. We can glance at a margin note, then look back at the main text. One speculative thought, written lightly. Could there be life on Earth with a separate origin? A shadow biosphere, hidden because it's built from different chemistry. It's a what if, not something we've found evidence for. Another idea, organics from comets and asteroids, sometimes called pseudo-panspermia, may have added ingredients. That's plausible, but it shifts the question. It doesn't answer where life began. We can let those speculations rest in the margin where they belong. We can stack a few small notes on the tabletop, one thought per slip. First, life's building blocks can form through abiotic chemistry. They don't require life to exist. Second, RNA can act as both carrier and catalyst. That's been shown in lab experiments. Third, multiple settings remain possible. Hydrothermal vents, surface wet-dry cycles. Different steps may have happened in different places. Fourth, we have solid evidence for microbial life about 3.5 billion years ago in the form of stromatolites. Fifth, thinking of life's origin as a gradual shift helps us avoid forcing sharp lines where they may not belong. Sixth, Luca wasn't the first life, but a successful descendant traced through what life shares today. We can slide those notes back into the book and let them rest. The lamp is still here, the page is still, and the room is calm. We've walked slowly through the question, noticing what's clear and what's still being explored. No urgency, no sharp turns. Just the ongoing work of researchers testing ideas, collecting clues, refining the story. The book doesn't need to be finished tonight. We can close the cover softly and leave it on the shelf for tonight. And the room can stay just as it is, quiet, steady, and kind.